Hello, and welcome to the Chem 1A pre-lab lecture for Experiment 9, Inorganic Synthesis of Alum from Scrap Aluminum. Our learning objectives today are to understand the stoichiometry of chemical reactions and learn how to balance reactions. After performing the synthesis of alum, we will practice calculating percent yield. Through the experimental procedure, we will review vacuum filtration as a separation technique. And throughout the experiment, we will focus on and learn how to safely handle strong bases as well as strong acids. The experimental objective is to synthesize the compound alum from scrap aluminum using potassium hydroxide and sulfuric acid in excess through two steps. The overall chemical equation is 2 moles of aluminum plus 2 moles of potassium hydroxide plus 24 moles of water and 4 moles of sulfuric acid will yield 2 moles of alum and 3 moles of hydrogen gas. Once we have performed the procedure and collected our alum, we will determine the percent yield of solid alum based on our initial input of aluminum. This is because, as I mentioned earlier, the potassium hydroxide and the sulfuric acid will be supplied in excess. Today's experiment is a two-step chemical reaction, and in multi-step reactions, the products of the first reaction become reactants in the second step. So in our first step, we will mix solid aluminum with potassium hydroxide and water, and this will yield potassium ions, aluminum hydroxide anions, and also hydrogen gas. The hydrogen gas I've left in black here to indicate that it is not going to be carried on into the next step. As a gas, it's going to bubble out of our solution and into the atmosphere of the classroom, and so it will not be carried over into the next step. However, the potassium ions and the aluminum hydroxide anions will be carried over. You will then add sulfuric acid, yielding more potassium ions, aluminum ions, sulfate ions, and water. And so now that we have products from reaction 1 becoming reactants in reaction 2, we can begin canceling out products that appear as reactants. So I'll begin with my potassium ions. They're products in reaction 1 and reactants in reaction 2, so those cancel out. Similarly, the aluminum hydroxide cancels out. In the final step of the reaction, you allow the solution to cool down, thus the alum forms crystals and precipitates out of the solution, allowing it to be collected by vacuum filtration. You will note that the reactants in reaction 3 are very similar to the products in reaction 2. However, the stoichiometry is different. In order to balance these reactions, we need to multiply reaction 3 so that the number of reactants of reaction 3 equal the amount of products in reaction 2. So we will simply multiply the entire reaction 3 by 2. This will yield 2 moles of potassium ions, 2 moles of aluminum ions, 4 moles of sulfate, and 24 waters, equaling 2 moles of alum. So you can see that once we balance all 3 steps of the reaction, 2 atoms of aluminum will yield 2 molecules of alum, or 2 moles of aluminum will yield 2 moles of alum. Now that we've balanced equation 2 and 3, we can cancel the products from reaction 2 with the reactants of reaction 3. And this gives us the net reaction of 2 aluminums plus 2 potassium hydroxides plus water plus sulfuric acid, yielding 2 moles of alum and 3 moles of hydrogen gas. Moving on, let's consider how to calculate percent yield. Percent yield is simply an expression of how successful your synthesis was. Percent yield is calculated as mass obtained divided by theoretical yield times 100%. And this is simply how much you collected divided by how much you possibly could have collected if everything went perfectly times 100. So you can see how that would be an expression of how successful you were. So as I said, percent yield is a measure of the success of the reaction. To do a percent yield calculation, the mass obtained is fairly simple to achieve. You simply weigh the amount of alum crystals that you get at the end of the experiment. That's what you obtained. The theoretical yield is a little more tricky. For the theoretical yield, we have to consider the balanced equation and the stoichiometry and the molar ratio between our limiting reagent and our product. To begin calculating theoretical yield, use the molecular weight to convert the grams of limiting reagent to moles. So in the case of your experiment today, the limiting reactant is the aluminum, the scrap aluminum that you begin with. So you will take the mass of aluminum, let's say you have about half a gram, so 0.514 grams, and divide it by the molecular weight of aluminum, which is 26.98 grams per mole. This would mean that in your reaction, you added a total of 0.0191 moles of aluminum. Because we balanced our reactions, we know that 2 moles of aluminum should be able to generate 2 moles of alum if all of the aluminum is consumed. So we use that balanced chemical reaction to find this 2:2 molar ratio to figure out how many moles of alum we could generate. So we take our 0.0191 moles of aluminum and multiply it by that molar ratio of 2 moles of product for every 2 moles of reactant. You can see that the units moles of aluminum will cancel as we have them on the top and on the bottom. And so in the end, because 2:2 is the same as a 1:1 ratio, we have 0.0191 moles of alum possibly synthesized. We are almost there at theoretical yield, because now we know how much alum we could synthesize. But percent yield is derived in terms of mass, so we need to convert from moles of alum into grams of alum. So we will take the moles of alum that we calculated from our molar ratio and multiply it by the molecular weight of alum. So remember, when you are calculating the molecular weight of alum, that it is a hydrate and it contains 12 waters. So the total molecular weight of alum should come out to 474.4-ish. So I used 5 sig figs here, so my molecular weight was 474.39 grams per mole. So multiplying this molecular weight by my 0.0191 moles gives me a theoretical yield of 9.06 grams alum. So backing up, if I started with 0.514 grams of aluminum, then the most alum that I should be able to synthesize is 9.06 grams. So my theoretical yield is 9.06 grams. Now I simply need to know my mass obtained. So in a hypothetical situation, assume you isolated 5.084 grams of alum from your reaction when you began with this 0.514 grams of aluminum, and keeping in mind that the aluminum is limiting because the potassium hydroxide and the sulfuric acid are in excess. So my mass obtained will be 5.084, and then my theoretical yield I just calculated to be 9.06 grams. So 5.084 divided by 9.06 times 100% gives me 56.1% yield. Note that I have 3 sig figs in my final answer because my theoretical yield only had 3 sig figs. And I need to use the least number of sig figs when I'm using division. Okay, so now that we have some of the theory behind us and understand our calculations, let's talk about the experiment. Experiment 9 is an excellent one for us to use a flowchart to help our understanding on what's going on and what reaction step is happening when and what it should look like. So I've made a little flowchart here so we can work through it together. You're going to begin with clean aluminum. This is either some aluminum foil that's provided by the stockroom or a piece of pop can that you would need to scour with steel wool at the beginning of the experiment. Either way, we're beginning with our sample of clean aluminum, and then we're going to dissolve it in hot 2 molar potassium hydroxide. If we were using a piece of soda can, we would need to remove the plastic backing at this point. However, if we are using aluminum foil, we do not need this step. While the aluminum is dissolving in the hot potassium hydroxide, hydrogen gas, as well as potassium hydroxide fumes, will be generated. So it's very important during this step of the experiment that all of the fume hoods are on and that the lab fans are on. So if your instructor has forgotten to turn these things on, make sure you ask them to, or else the air will become quite toxic. Other products of this step are our aluminum hydroxide anions and our potassium cations. These two reactants will be carried over into the second reaction. However, before we move on to that step, we need to continue heating the sodium hydroxide solution until the volume is decreased by about half. This will cause the potassium and aluminum hydroxide ions to be concentrated in the solution. You will next allow that solution to cool slightly and then filter it through glass wool to remove any non-dissolved particles. These could be remnants of plastic backing if we used the soda can, or other insoluble impurities in the aluminum foil. The next step is to place our solution on an ice bath and allow the solution to cool down while scratching the base of our beaker with a glass rod. This cooling and scratching allows the alum to crystallize and collect at the bottom of our beaker. We will then set up a vacuum filtration apparatus to collect our solid alum. To assist in drying and washing of the alum crystals, we will rinse with ethanol and water mixture. This mixture will remove soluble contaminants and also dry rapidly due to the ethanol component. We will then be left with our solid alum crystals. The last step is to weigh these crystals and then go on to calculate our percent yield. Couple technical tips. Remember that you need to know the mass of aluminum that you begin with, not the mass of aluminum can. So if you are using a soda can for your sample, it's really important to deduct the mass of the plastic backing that you fish out during the first step where we're dissolving the soda can in the potassium hydroxide, and to weigh that piece of plastic and deduct it from your original mass so that you can find the weight of aluminum used. Remember, this weight of aluminum used is going to be used to calculate your theoretical yield and is really important for your percent yield calculation. It's also important when rinsing to use only minimal amounts of distilled water. This will avoid diluting the reaction and help to ensure that you get the best yield possible. So when you are using the glass wool to filter after the potassium hydroxide boiling step, just use 1 to 2 milliliters of distilled water to rinse your sample through that glass wool. The last technical tip is it might be a good idea to pre-weigh the filter paper that you use for vacuum filtration so that you can deduct the mass of the filter paper from your alum crystals. Rather than having to scrape the crystals into a weigh boat, you can simply weigh the filter paper with the crystals and then deduct that initial mass of the filter paper to get the mass of alum collected. There are some significant dangers in today's experiment. You are going to be working with Bunsen burners and also with strong acids and bases. So let's review some safety hazards and precautions. Remember that a Bunsen burner is an open flame. So it's very important to make sure that all long hair is tied back away from your face and to take caution with the flame and hot objects. Be aware of what you are doing. Remember that just because you've removed a beaker from a flame doesn't mean it's instantly cool. Allow it to cool before touching. Also, never leave your flame unattended. If you need to get a new piece of equipment or supply, send your lab partner to get it while you take care of the flame. Otherwise, turn off the flame to fetch the needed objects. The wire screen that's indicated in your lab manual procedure is included to evenly distribute the heat of the flame onto the beaker. It's very important that the flame does not directly contact the beaker, but rather contacts the wire screen, and then the heat radiates from the screen onto the beaker. It's also very important to clamp the beaker to the ring stand and not simply rest it atop the wire screen. For the strong acids, sulfuric acid, and the strong base, potassium hydroxide, these are both highly corrosive chemicals and can easily cause burns on exposed skin. Make sure you're wearing gloves in addition to your usual lab coat and goggles. Avoid splashes and always look around you before moving with a container full of potassium hydroxide or sulfuric acid. You should never fill a container near to its capacity with these solutions, but rather use a larger container if you need to move from the fume hood to your bench, for example. If in the event there is a spill, call the instructor over, as there are special supplies in the classroom for cleaning up these types of spills. Do not simply use paper towels. In the first step of the procedure, when you are heating the potassium hydroxide solution, heat it only gently. You do not need to use the hottest part of your Bunsen burner flame for this step. You just need to get the potassium hydroxide up to a gentle boil. And if it begins to boil too rapidly, simply push your Bunsen burner aside until the bubbling subsides, and then you can place the flame under your beaker again. Once again, ensure that the lab fans and fume hoods were turned on at the start of class before any experimentation begins, so that the hot potassium hydroxide fumes and hydrogen gas do not collect in the lab. And lastly, when it's time to add your sulfuric acid to your potassium hydroxide solution, add it very slowly and be stirring as you add. You may need to use a lab partner here, where one person is pouring while the other person is stirring. This concludes our pre-lab lecture for Experiment 9. Please be careful and have fun.